we are finishing up kinetics as far as these integrated rate laws. We're at lesson 5, which is page 11 of your study guide. All right, we've looked at first order reactions, and now we're going to do the same thing with, hang on. Now.
It's okay, you can just erase this part of the video.
No, you'll get to see the whole thing.
Oh, okay. No, I will.
You can take this to the library. Okay. All right, and you can use a calculator, and I've got a periodic table there. All right.
High definition Malay.
Okay. So, a second order reaction. Let's look at the differential rate law, which is rate equals. And with these, all right, with these integrated, we're always just doing it with one reactant to make these easier. All right. So if we integrate that, we're just going to say it magically integrates itself. We actually get this. 1 over the concentration at a given time is equal to KT plus 1 over the concentration initially. Okay, that is the integrated. That is the relationship between concentration and time. Remember, the limitation of this was it only told you the rate at which it was going. So you couldn't make, you know, how long does it take to get to a certain concentration. Differential rate law won't tell you that. Just tell you the rate. Okay, now, the relationship, the linear relationship, then obviously y equals mx plus b. You know, you put that on a graph, and the graphic relationship then of a second order reaction is time versus 1 over the concentration at a given time. And notice this is positive. It is the only one that has a positive slope on its graph. So a second order reaction is the only one that graphs with a positive slope. All right, and they might have it just fill in the blank. What would go here for a second order reaction? And so you need to know. But if you know the IRL, that just makes sense. All right. And remember that the units of K for a second order reaction then are going to be 1 over molarity times second, or molarity -1 seconds to the -1. Because the units will be unique for the order of the reaction. Okay, so with that in mind, let's just look at a few problems. You know, this is just plug and chug into that particular equation. And this equation is on your reference sheet that you'll have access to, so you don't have to memorize it. All right. All right. I plus I goes to I2 is second order reaction with a rate constant of 7 times 10 to the 9th. If the initial concentration of I is 0.086 molar, calculate the concentration after 20 minutes. All right. Well, we know that time is seconds, so 20 minutes times 60 is 1200 seconds. Remember the units of your equation. All right, so we just put that information into our equation. 1 over 0.056 molar is equal to 7 times 10 to the 9th, molarity to the -1, seconds to the -1, times 1200 seconds, plus 1 over 0.086 molar. Okay. Now we just simply do the math. And the math then gets us to the concentration of I after 20 minutes would then be 1.19 times 10 to the -13th molar. And actually everything they gave us was in 2 sig figs, so probably actually more correct to put 1.2. However, they give you plus or minus 1 sig fig. So just always be cognizant of your sig figs. Or they could say, how many minutes does it take for the concentration to drop to 0.056 molar? All right, well, actually this should have been 1 over A, I'm sorry, I missed.
It was fluctuating over
Yeah,
something.
all right, sorry about that. That's the next one. I said. Cut, take 2, let's start all over. No, all right. This one is 1 over 0.056. I was going, gee, that sounds familiar. And 7 times 10 to the 9th. Molarity to -1, seconds to the -1, times time, and from this equation, what will the time be? What units? What?
In the equation or
Yeah,
something?
seconds, because the equation will solve for seconds, all right? Always remember that. And our initial concentration was this. Okay, so when we do the algebra, we get time equals 8.9 times 10 to the -10th seconds. They wanted it in minutes. Or 1.48 times 10 to the -11 minutes. And that makes sense because we really didn't drop the concentration that much, did we? And it's going to go fast. All right. Okay. Half-lives of a second order. Remember we said with first order that half-lives were consistent, and because mathematically the concentration dropped out, for a first order we saw the natural log of 0.5 over the K. All right, that was a first order. Those half-lives are consistent, and they are not dependent on the initial concentration. And now we're going to look at what happens with half-lives of second order reactions. And once again, remembering that all nuclear reactions are first order reactions, and that's why they have consistent half-lives. All right, well, let's do the same thing, and you don't have to know this, but it's just nice to see it, to see how you get the end equation. If we put 1 over, 0.5 times the initial concentration is the half-life, right? What time does it take to get to half of the original? Is equal to KT plus 1 over the initial concentration, correct? So that's what it would look like for a half-life. All right, well, 1 over 0.5 minus 1 over. Are you with me so far? Okay. 1 over a half is really 2, correct? All right, so 2 of these minus 1 of these simplifies to 1 over the initial concentration is equal to KT, which is the half-life here, right? Or the half-life is equal to 1 over the concentration K, right? Okay, so this is what you would have to do to get the half-life of a second order reaction. So 2 things that make it different than first order, okay? First of all, it's going to be dependent on the initial concentration, isn't it? Right? The half-life is going to be different depending on what we start with. That wasn't the case the first order. A first order was not dependent on initial concentration because the concentrations canceled out mathematically. This is not important for you to know. I just like you to see how, we got to it. All right. Another thing is that, well, the 2 things, the half-life is not consistent and it is dependent on the initial concentration. So we can see that a second order reaction has very unique properties from a first order reaction. a first order reaction had a negative slope, and you had to look at the natural log of the concentration versus time. Its half-life was consistent and not dependent on the initial concentration. Now saying the same thing for the same variables for second order. A second order, it has a positive slope linearly, and it's 1 over concentration versus time. The half-life is very much dependent on the initial concentration, and the half-life itself is not consistent. All right, because once we get to half amount, that'll change that, which will mathematically change it. So we can't do like we do with nuclear equations, where we say, okay, if 5 seconds is a half-life, then every time this goes in half, it'll be another 5 seconds. That's what we mean by a consistent half-life. Because every time we break this in half, we're going to get a different numeric value. So second order reactions have different properties than first order reactions. Okay? If we were just given a group of data, like we see at the bottom of page 11, and we were just given, here's NO2. Its initial concentration is 0.01. By the way, how do I know that's an initial concentration? Very good, all right? Sometimes things are so obvious we make it hard. What's the initial concentration in this? I don't know. It doesn't say the little zero, well, okay, at time 0 is when it would start. All right, the initial concentration of this, and we're looking at what happened to the concentration as time goes by. All right, and if we were saying what order reaction is this, well, we would look. We'd probably start with, well, let's see if it's a first order reaction. If it was a first order reaction, I would take the natural log of those concentrations. If it was a first order reaction, I would take the natural log of the concentration of NO versus time. And if I got this, it's a first order reaction. Okay, if I took the natural log of NO versus time and I got dots all over the place or something, then I would go, whoa, well, that's definitely not a first order reaction. So then I'd move on and say, okay, let's see if it's a second order reaction. If it's a second order reaction, I would invert those concentrations. I'd take 1 over 0.01. I would take 1 over 0.0088. All right, because a second order reaction will graph 1 over this concentration versus time. And so I'm going to take 1 over, and I would get, 100. I get 113.6, 126.6, 140.8, 153.8, 196.1, 208.3, 238.1. All right? And then obviously I'd have 0 to 300 seconds where I time this. And I would, painstakingly figure out where I would touch the graph button on my calculator. And I would notice something happen. I got best fit line, obviously. You got if you see a pattern. And I would say, this is a second order reaction because I get a positive linear relationship when I graph 1 over the concentration versus time. Okay? That is unique to a second order reaction. And then I'd also, because of this equation, I would know the slope is k, isn't it? So I could graphically, y equals mx plus b, I could graphically determine, change in y over change in x, or is it change in x over change in y? Right? I could graphically determine what the rate constant is for this reaction. Because the line, the slope is the k. Okay?
So bad.
Yeah.
We got it all on video.
All right. So now let's let's look at zero order reactions. All right, the differential rate law of a zero order reaction, and remember this is looking at having one reactant because we're, for the sake of argument. So it would be rate equals K times A to the 0, which means what? Rate equals K, doesn't it? So does the initial concentration matter? It just happens, bam. Doesn't matter how much we have, it just happens. All right, and the rate will equal whatever the rate constant is. Right? There's no other reaction that does that, because everything else mathematically has concentrations in it. This one doesn't. All right, so the integrated rate law for this, okay, this gives us the rate, and it tells us the rate it'll go. It doesn't matter the initial concentration. If we integrate that, we get the concentration at a given time is equal to negative KT plus the concentration originally. Right? Notice again that this is going to, if we look at it linearly, what is the linear relation of a zero order reaction? It's just concentration versus time, and it will have a negative slope. Right? So both a zero order and a first order will have a negative slope. It is a second order that is unique and that it has a positive slope.
Did you mean for that to be A sub T concentration on the graph?
Yeah.
Concentration of K on the graph.
Oh, yeah, that looks like a K, doesn't it?
Yep.
Really bad A.
I don't even know what that is.
Like it could be
Any letter it wants.
whatever it wants to be.
There. Is that neater?
Yes.
All right. Man, an Asian who can't recognize an A. Oh, got that on video, don't we? Yeah. Oh, all right.
I think you're outnumbered, Miss Wayne.
Yeah, yeah. Not if we count the whole class.
That's
Hey,
still half and
4-4.
Oh,
Yeah.
Kitty's back there. I forgot.
No, 3-4. 3 to. No, wait.
half. It's 4 to 4.
That's why you're a chemistry teacher.
Cut. Let's start over. No.
Yes, Michael is also Asian.
Hannah, does she count? I mean,
Yes.
she's adopted.
They're both adopted.
Oh, okay.
Oh,
Well, then I think we kind of got the,
no, at least I can use chopsticks.
if it's
You really
nature,
haven't
nurture,
imagined it. I can use chopsticks.
Yeah.
See, now she's
I'm
also
very
Asian.
Asian.
All right. Just be quiet back there. That's going to help the cause. All right, you're the great white hope, so let's not talk about chopsticks.
Forget this all in video.
This is the reason why Liv wanted to join our lecture.
This is, yeah.
Yeah.
I've never heard that
You can
expression.
relive this moment over and over and over and
Oh, okay. Anyways, so let's summarize to make sure we have it, because sometimes we don't. And I think we do. So I got a little fill in the blank chart, all right? Let's summarize this. The pertinent things for a zero order reaction. The differential rate law is rate equals K times A. There we go. Oops,
No.
to the 0. All right. The integrated rate law then is just the concentration of A sub T, lowercase k, T plus concentration of A. All right. The slope of the line is negative. The units of a zero order reaction would just be the units of the rate, wouldn't it? And what's unique is rate is not dependent. Rate itself. Okay, it's the only reaction where we can say that, because we go on and on and on about one of the things that speed up a reaction is concentration, right? Right? This is one where it's very unique. It doesn't matter how much we have, it just happens and it'll happen at the same rate. for a first order reaction, the differential rate law is rate equals K times A. If we integrate a first order reaction, we get the natural log of A at a given time is equal to negative KT plus the natural log of the initial concentration. Okay. This one also has a negative slope. Its units, the molarity cancels, right? And then what is unique about a first order reaction is the half-life. That's what's unique about it. It is consistent and not dependent on initial concentration. Oops, I forgot the half-life column,
Yeah.
didn't I? Okay, the half-life of a zero order, I'm going to put it over here, okay? Half-life is the concentration of A over 2K. I won't show you the math on that one. Just trust me. All right. The half-life of first order is we have that 0.693, which is the natural log 0.5 over K. All right, and then lastly, a second order reaction. The differential rate law is rate equals K times A squared. The integrated rate law is 1 over the concentration of A at a given time is equal to positive K times time plus 1 over the initial concentration. Notice how similar. So if you have this one on your reference sheet, so just remember 0 is going to be very similar. These flip over and that's the opposite. All right, so you don't have to memorize that. However, I doubt if they'll have you use this since it's not on your reference sheet. They're really going away from just memorizing equations. All right, the half-life calculation for a second order reaction is 1 over. And then, notice how that is different from 0. A second order reaction has a positive slope in its linear relationship. The units are molarity to the -1, seconds to the -1. And finally, what is unique about a second order is that the slope is positive. All right, so this is the information that you need to know. Probably the only thing you need to know for a zero order reaction is the units, and that the rate is not dependent. Otherwise, it comes down to having to memorize a math equation, and the exam is veering away from that. Okay, so how to help yourself out on the reference sheets. Okay, right there I show in your notes what the kinetics portion on your reference sheets you have available to you during the whole exam. Under the heading kinetics, say, all right, notice that it is written a little bit differently. It has this. Okay, well, what they did was they put both concentrations on one side. I have shown it to you in the equation of a line, right, where you just move this over there, right? So you can rewrite this and just know, see how it's the exact same thing that we learned. All right, I just think it has more meaning when it's written in the equation of a line. I think the exam does that just to confuse you. Okay, but what is given to you is on the left side. I want to show you how to modify it. So the first thing that I would do when you get your exam is I'd go to that reference sheet and I would do this before you start. All right? And first of all, I would make sure you knew which order those things start with. So right next to the LNAT, I would put first. And then right next to the 1 over concentration of A to the T, I would put second. So I know that equation is for a first order reaction and the next one is for a second order reaction. And then they give you the half-life of a first order equation, don't they? So I would write first, right next to it. Okay? Now, if you wanted to, you might just quickly do this, but I don't think this is, this is for a 0 order. Okay, they don't have it included, right? But then what I would also do, just so I remember, is I'd put the slope. This is going to be negative, this is going to be positive, and this is going to be negative, all right? Well, and here, right next to the half-life, I would put consistent and not dependent on initial concentration. So this isn't really important, but if I were you, as soon as I received that test, after I put my name on it and I opened it up, I would open that reference sheet and I would put that beside it. And so when you're doing that, when you get to multiple choice that are easy, and then you can just make, a dyslexia on the what's what, I don't even know how to use this chart, you can look at it and it's just staring at you. Oh, that first one is first order. That second one is second order. That half-life is for a first order. And what does it mean, And heck, if you even wanted to go one step further and put the units there, so you knew, or just go units, so you don't screw those up. All right, but help yourself out, okay? Because once again, this is March 2nd, you take the exam May 4th, and it's comprehensive. Are you going to remember this with this clarity that day? No, so help yourself out. All right, one more thing I want to say about graphs, and I think they have phased this out of the AP exam. It used to be on the reference sheets, and it is no longer. All right. And that is the Arrhenius equation. We talked about Arrhenius back in acids and bases, said how he got no respect, but the guy was brilliant, right? And he came up with an integrated way of looking at, mathematically, the relationship between a rate constant and activation energy. Okay? He could tell you, just remember we said activation energy is the nudge you need to give a reaction. He could actually, mathematically, came up with an equation to be able to calculate the nudge you would have to give any reaction, which is really amazing. Now, the equation he had, and I'm going to write the equation, but I want you, we're just going to bottom line by what do you conceptually need to know about this equation, all right? You do not need to know the equation. I'm just going to show it to you, okay? The natural log of the rate constant is, this is the activation energy over the ideal gas constant in the different units, over 1 over temperature, plus the natural log of A. And A is a factor that takes into mind the complexity of the molecule for that, one of the things is the orientation. I mean, you can even mathematically calculate the relationship between the complexity of the molecule and what the chances of a successful collision are going to be. And that's the precise way in which matter interacts. That is just so astounding. I mean, it is just amazing. All right, well, once again, I've written this, y equals mx plus b. All right, so the slope of the line is going to give you the activation energy, which is cool, in this relationship. You can also rearrange this equation at 2 different temperatures, and you can mathematically determine, remember how we say K will change at a different temperature? You can mathematically determine how much it'll change. By this equation, putting in 2 temperatures, you can know how the rate constant will change. I mean, that's really astounding when you think of it. Now, do you need to know this? And this is the relationship. The natural log of the K times the inverse in time will give a negative slope. And this slope will give us the activation energy. So here's what you need to know, not this, right? This is what this gave us. It told us that as the activation in energy increases, K will decrease. And that makes sense. The more energy it takes, the more the concentration has to be to get it to happen, doesn't it? Because remember, K is that rate constant. And as temp increases, K increases. And that makes sense. Remember, this is going to be rate is equal to K times whatever concentration. All right, as the temperature goes up, this has to go up, which means this isn't as important, and that makes sense. Temperature goes up, they're moving around, but as the activation energy goes up, the energy at which they have to, this goes down, so we need to get a lot more of this, right? So it's just understanding how the activation energy and K are connected and how temperature and K are connected. And you do not need to use this to explain it. It's just point and fact. Point and fact. And I don't even know, I do not even know if this will be tested anymore. All right, I just want to throw that in just in case. But I'll tell you what, if this would be the thing that separates 5+ from a 5. You could still get a 5 on the exam and not even understand what's written here, okay? But it is pretty impressive that somebody came up with the math linking temperature, activation energy, the rate constant, and the complexity of the molecules. Just really amazing. Everything reacts in a mathematically precise way, which is pretty cool. And I think that ends our unit. All right, the rest of those lessons are on video. So we'll stop there.